Hello everyone, I'm Mohammad Keshavarzi. I'm a PhD candidate at UC Berkeley. I work at the FHL Vive Center for Enhanced Reality and also the XR Lab. And today I wanted to talk about how generative modeling and its applications can benefit future spatial computing experiences. Okay, so let's start. So as you all know, spatial computing has emerged as a promising platform for next generation human computer experiences, and it's hopefully going to change our lives and the way we interact with computational systems, the way we play games, the way we communicate, are all things we're looking forward to in the spatial computing era. Now, when you think of it, it's not just that spatial computing allows us to see things in 3D instead of a 2D screen, but it actually is some kind of a connection between us and our surrounding environments and virtual environments. So it really gets us closer to the objects and other entities around us. In other words, spatial computing experiences executed on the grounds and the context of our own environment. All the geometry, the structure, and all the functional relationships present in our own environment make up the visual foundations for spatial computing. And as I said, there's a very extremely exciting body of work going on in the field of telepresence. In other words, sharing spaces or bringing other people to our own spaces is really going to change the way we all will communicate. And hopefully spatial computing would play an important role in future telepresence workflows and understanding how these systems will interact with people and their individual spaces. It's a key step in the direction of utilizing this technology in future communication systems. Okay, so when we're talking about spaces, it's really important to keep in mind that our surrounding spaces are very different from each other, both in terms of their geometrical properties, such as size, layout, and material, and also the functions they serve. Yet, when we think of future AR applications or mixed reality applications or even VR applications, one of the main challenges that can be highlighted is that there is somehow a design barrier between the content developer and the users. So what do we mean by design barrier? Well, content developers are not aware of the exact properties of our rooms. So when you're a spatial computing developer, you really don't know what and how your content will be displayed in the context of other people's rooms. So you don't know that, the experience and the development you're doing, how would it show up and how would it look like? And how much occupied space does the target rooms have? Or how much horizontal surfaces, reflections, and colors and materials? And these are all unknowns to the developer and the content designers. We also had this a similar problem before when we were trying to develop one type of content for different screen sizes, for different target devices. So right now, websites use a technique called responsive design. You write one set of code, but it's basically responsive to different screen sizes, different resolutions, and we might think, spatial computing can also go in that way. But the problem is, 2D screens come with a lot of difference between, what really is in our 3D environment. There's 2D screens, it's just some rectangular, black, empty screens, while in 3D, we have this very irregular geometries happening around us. There's so much ups and downs, and there's so much obstacles that it's not that easy to predict and lay out the content way before actually seeing and analyzing the scene. And of course, the technology to fully understand the scene and its geometrical property, the very high quality mesh extractions, the semantic segmentations, what functions and how they work together, we still have a long way to go, and there's a lot of challenges to kind of overcome. So in general, that's what we're talking about, the design barrier between a developer and our spaces. And if we don't come up with a system in between, it's going to be pretty hard to actually solve this issue. So what's really important is not only that we need to think about how one single content developer or a company wants to develop for our spaces, but going back to the discussion of having mutual telepresence experiences. Even individuals, even users of spatial computing experiences would have issues in communicating together when they don't know and are not aware of each other's spaces. So today, with a focus on generative modeling, I really want to talk about the concepts of, can we come up with a way to contextualize our virtual experiences in the spatial computing platforms. So I'll try to cover two directions of this topic. First of all, content augmentation, and also mutual spaces for users that are connecting remotely and are not aware of each other's room. So let's start with a content augmentation of an unknown target scene. Let's open this problem a little more. Say we have a target room of a user. On the left, you see a top view of its living room, and on the right, we see an eye-level perspective view. And for our spatial computing experience, we want to add a virtual object or a specific content to our physical room. And for the sake of example, and just to show some meaningful relationships, let's just say we want to add this chair to the target room. Okay? So as you see, the main challenge is, in theory, the chair can be placed anywhere in the room, in any direction and any location, which may cause some geometrical conflicts. And even if it's not causing some conflicts, it may not be placed within the suitable context. So you see examples of what I just mentioned here. On the left, you see the chair is conflicting with other chairs and sofas. And on the right, you see it's inconsistent with the context. It's just looking in a direction that you would never generally place a chair like that in a room. So let's talk about a little background of how others have tried to address this problem. In general, we have two main strategies for addressing the scene augmentation challenge. One is coming up with a procedural model, and two is learning from prior examples. I'll talk about in detail of what each of these means. So let's start with procedural modeling. So procedural modeling, we can just define it as rule-based modeling. Okay, so any kind of automatically generated asset based on a limited set of user-defined input parameters can be defined as procedural models. Okay, so we come up with a set of rules. These rules can be hard-coded in the system, or it can actually have a user in the loop. So let's see some examples. Okay, so this work was published by Tobias and Schwartz in the Computer Graphics Forum in 2009. And it shows how an agent-based procedural model is utilized for each object to find suitable parent objects and to place and orient itself properly. Okay, so the agents are given the object size, its bounding box, the class of the possible parent objects, and basically everything they need to know to find what the best parent and the best position in relationship to the parent can be. So in other words, the ideal relationships between the objects are hard-coded, and the system goal is to find the best arrangement possible to achieve a higher number of acceptable parent-to-child relationships in the scene. On the middle, you see the generated tree graph of the system, and on the right, you see some results of their system. So when we move forward, we see another study here by Paul Merrill and his colleagues that utilize procedural modeling again for synthesizing scenes and generating plausible scene alignments. This work was published at ACMTOG, and over here we see, in addition to very straightforward relationships like object adjacencies and parent-to-child relationships, the authors have actually hard-coded functions such as circulation scores, conversation possibilities, visual balance, alignments, and these kind of qualities. And these are basically some of the rules interior designers intend to implement in their designs. And the authors have basically extracted these qualitative rules from textbooks and translated them into some sort of quantitative embodiment in a procedural code-based fashion. But with these, looking at these two studies, which are honestly just examples of many other papers which utilize procedural modeling for generating environments and scenes, with all the success they've shown, the results typically differ from a naturally arranged scene we really see in real life. And we can attribute these differences, to two main reasons. One, design is generally considered a high dimensional task. So what do I mean about high dimensional tasks? It's like you just don't want to achieve one goal in this process, right? There's multiple different goals that come up in the design process, and you want to basically approach them all together, and the human designer, is responsible for prioritizing them. That's why you see so much different designs, and some designs have a strong aspect in one criteria and some don't. Now, if you give this to a system, you have to do the prioritizing for them, and it's not always easy. And many attributes may cause conflicting arrangements with each other. So many models end up defining weights and arbitrary prioritizations, which cannot be generalized in many cases. The second drawback is, the systems cannot capture those very small, unique natural qualities. These qualities generally emerge in the process of time and human engagements. People refer these qualities to qualities without names, and it's really absent in such models where everything is rule-based and hard-coded. So this takes us to the second method. And the example-based modeling method, or the data-driven modeling method, has gained a lot of momentum in the past few years. In these set of methods, instead of hard coding a set of procedural rules and patterns, we set examples for the system and expect the system to learn from them. Okay, this way, we're not bound to a set of discrete rules, and we don't need to arbitrarily weigh and prioritize between them. So this is one of the early successful papers, also published in ACMTOG by Matthew Fisher and his colleagues at Stanford. The idea is pretty straightforward. You give a set of example scenes as input to the system, and the system starts synthesizing new scenes, very similar to the example scenes, by learning from the relationships and constraints from a set of prior scenes. Okay, so you have like some input scenes, the system starts modifying them using the constraints you see here in the middle from a database, whole other sets of scenes. What they do is they just develop two probabilistic models for one, object relationships, and also an occurrence model, basically knowing that what object should be added or not added to the scene. So the first one, again, it's helps to understand what object should be available in this generated scene, and the second arrangement model is basically where those objects should be placed. So in addition to coming up with probabilistic models for object arrangement and also occurrence, there's also another very interesting direction that has been introduced in scene synthesis literature that also takes into account human activity. And this is very interesting when you look at it in data-driven generative models. For instance, this work, again by Fisher and his colleagues, start with a 3D scan and learn the scene template that describes different activities that can take place in environments and generates kind of a rough geometrical layout of the scene. So you have two representations: one, the rough geometrical layout, and also an activity map. Based on these two trained models, you can generate new synthesized scenes that respect the activity and geometrical constraints of the scene template. So in addition to pairwise relationships between objects, right, you have a human activity also involved in the training of the system. Okay, so the question comes in, like, what data sets people use for this? And I'll try to define these as three types. One, we have synthetic data. There's a data set, actually, it's kind of in a dispute situation right now, but it's called SunCG. There's around 45,000 human-generated scenes extracted from a website called Planner 5D. And basically, people have gone on that website, tried to design their own homes, and this is being used as a data set. There's a lot of discussion whether, this data set can be really a good sample set for training data, and we'll talk about this later. But it has a lot of data points, so it's really helpful for approaches like deep learning. The second type, which is kind of emerging set of data sets, is also fully scanned homes, and you can imagine how hard it is to kind of scan all these scenes. The Matterport 3D is a very good data set in this regard. There's a bunch of other data sets, but I guess the probably best open source available data set right now is the Matterport 3D. You also have, some new work. I brought an example here, like PerspectiveNet, a 3D object detection. So you give a RGB, and the system actually extracts the bounding boxes, and it comes with some level of accuracy, but in general can be really useful in our field of scene synthesis and really understanding the relationship between objects. So given that background information, I wanted to quickly go through a recent study of ours and how we approach the problem of scene augmentation using scene graph writers. So again, same slide. We have a spatial scene representation. A previous semantic segmentation system would help us understand the semantics and the bounding boxes of our objects. So this is a given in our system. Now, once we have these bounding boxes, we allocate each object to a node and their relationships as edges of a graph. And these relationships can be positional and orientational. So it's like how two objects are related towards their position, whether it's an edge of the room or it's in the middle of the room, or are two objects close to each other, or whether it's facing, whether it's towards the center of the room, or similar directions. We extract all these information from the objects in the scene and generally come up with a spatial representation graph that describes all the topologies happening in the scene. Now, the idea is, when we start exploring the different positions a new object can be placed in, we generate new scene graphs for each instance. And our system is able to find the highest probable plausible scene in all the kind of sample positional or orientational points we have. And the question comes, how do you come up with this probabilistic model? Well, we train it based on a previous knowledge model. So we go through all the, our training data set in the Matterport data set, and we extract the scene graphs from it. So once we have the scene graphs from our data training split, we come up with a knowledge model that basically guides our probabilistic models for understanding which layout would be the most plausible layout in the samples. So going back to the data set, yes, we use the Matterport 3D data set, and there's a lot of discussions of why we did this. Again, we talked about those natural design occurrences that really happen in the integration of time and human activity. And you see this really happens in our real-world environments. And synthetic data sets typically don't capture those environments. Even data sets that are generated by human designers, not just like ordinary people, but people that are, for instance, architects, tend to have a lot of difference between what they were initially designed and what they end up to after people living in them. So it's really important to kind of have that in mind. Okay, so here's also a visualization of all our relationships in both positional and orientational features in our data set in the Matterport 3D. And you do see some interesting observations over here. For instance, the bed is usually towards the center of the room. Over here you see on the left, you see the storage is typically in the corner or at the edge of the room. It doesn't really happen to be in the middle of the room. And in general, we're trying to really show this kind of a visualization of our knowledge model. Okay, so let's show how our system works with a bunch of experiments. We have an empty room over here. This is the top view. We can extract the spatial representation graph, the scene graph, which we discussed from this target scene. And when we want to add a bed, we can basically sample the whole room, the possible positions, and visualize a probability heat map. Over here, you see the darker the red, the more probable the object can be in that location. And also here, you see radial visualization for the orientation probability. The greener, the higher chances that the bed, when placed there, would be plausible. So if we go through those two models, the placement model and the orientation model, we can place the bed over here and you see the perspective view. Over here we have a chair that we want to add, a bed, a desk chair, a coffee table, and also a kind of drawer, all placed in pretty plausible placements. We can also look at how we can place multiple set of objects. Over here, say we want to add a bed, drawer, and a sofa to the room. Same process, we can generate the heat maps. And as you see, when we augment the objects to the scene and we compare them to the ground truth, we do have some interesting observations. The bed, for instance, is placed in slightly different position, but again, it's still plausible. It's probably finding some relationships with the drawer on the left, but still you see the scene synthesized on the left can be totally possible and totally plausible from a user perspective. Here are some other examples. When we compare with the ground truth, the top row, we see a pretty similar arrangement. The row below, we added another coffee table in addition to what was already in the scene. And again, we see some plausible results. Okay, so in addition to qualitative experiments, we also come up with how we want to evaluate our system in a quantitative fashion. And this is a very interesting question you need to ask in any kind of research project, that what's the best way to really show the strength and weaknesses of your system with a set of experiments that kind of can be also compared with other systems as well. This is an experiment that we're doing. So given a ground truth scene, we take out one object. That scene that the object is being removed from will be served as an input to our system. And we would like to place the object that we removed from inside the scene. And so once we've placed it, we compare the distance error between our augmentation and the ground truth. So here are the results of the experiment in an ablation study setting. In our ablation study, we observe how the system performs with the presence and absence of different features in our proposed scene graph representation. On the left, you see the cumulative distance error between our top prediction and the ground truth. And on the x-axis, we have the distance in meters. And on the y-axis, we have the percentage of the scene augmentation instances falling below that error threshold. The right figure holds a similar setting, but this time, instead of comparing the ground truth with our top prediction, we compare the ground truth with the closest of the 5 positions. And the reason we use top 5 is exactly as we mentioned, since the object augmentation may have multiple correct plausible solutions, we would like to make sure we don't limit our evaluation to only the top prediction. So in addition to numerical experiments, it's also informative to basically ask users what they think. And this is the way we kind of designed our experiment. So if you have original ground truth, again, in our case, because we're using Matterport 3D data, we took scenes from that data set and we reconstructed the whole thing in Unity. So it's like a simplified reconstruction. Now, we designed 5 levels of our reconstructed scenes to randomly be shown to the user. The first level is when we place an object just randomly in the scene. Okay, so here you see some probably geometrical conflicts and strange topological relationships happen. In level 2, it's the same random position, but only in open spaces. So we avoid conflicting geometries, but the system won't come up with a plausible way to really show the relationships correctly. Level 3 is SceneGen, our approach. Level 4 would be our approach with a heat map, and level 5 would be the ground truth. And so we randomly show these different levels to the users. And here's our user interface of how they interact with our experiment system. Basically, they click on Add the Furniture, and when the furniture is added, they just give a score from 1 to 5 of how plausible the furniture placement is. So here's some results. It's pretty promising. You see that people aren't giving very good scores actually to level 1 and level 2 because random placements, and they weren't looking really good. You see a pretty small difference between our system and the ground truth. I guess this shows that our system is generating some plausible scenes in the masses and in the perspective of our participants of our user study. Now, we can also compare SceneGen with the ground truth, not only in terms of the general placement, but also by object category. We do see over here, for instance, the chair in SceneGen may not always work as good as the ground truth. Turns out, it's more of a subjective matter how you place a chair, because, there's probably a lot of possible and even better placements that users thought could be placed than the ground truth itself. So in addition to asking the user participants to give a score from 1 to 5 to the plausibility of the scene, we also asked them to actually adjust the augmented objects to a position that they thought it would be better. You see this plot in this figure shows the distribution of those adjustments by the users in red and the distributions of our top 5 predictions in green. What we're trying to kind of say in this figure is, again, it's not just one position that would be the ideal position for different objects to be placed in the scene. And there can be multiple regions in a given scene for that object. And SceneGen, in some cases, is doing a pretty good job in capturing those. And we can see those regions also captured in users' preferences in the scene augmentation positioning. We also develop an augmented reality application for this system. The idea is, if a user wants to augment an object in a scene with our system, it would be much more easier, much more faster, and more awareness of the spatial relationships of the scene itself. So in this video, you see first of a manual placement without our system. It takes some time for the user to come up with the best location and position of these certain objects that can be accessible through the menu of the augmented reality app. And compared with our contextual placement in this video, you see these heat maps basically showing where the objects can be placed. Okay, so we talked about how content augmentation can happen in spatial computing experiences. Now let's talk a little bit more about the concept of finding mutual spaces. Okay, so this work called Holoportation, developed at Microsoft Research, is one of the many great examples of how mutual space can be preserved in augmented reality or any general spatial computing setting. Look how the presenter here, Shahram Izadi, steps back from his ground to allow his daughter to move around the table. I was personally very inspired by this work the day I saw it back in 2016, and it illustrates a very bright future of how telepresence systems can be utilized for remote communication. But if we pause the video for just a second, we do see some critical issues. First off, the amount of space allocated for this experience in both rooms is pretty large. And if we look closer, we see some markers on the floor indicated that objects of these rooms, the chairs and the table, were manually calibrated beforehand. But those settings may not really be feasible in our everyday environments, right? to have large and accessible open spaces without any obstacles, and each time manually calibrating our surrounding furniture with each telepresent participant without actually knowing how other spaces of those participants looks like. So it's fair to say, with our current real world environments and surroundings, collaborative spatial computing has spatial limitations itself. So let me open this up a little more. Say we have 3 individuals wanting to hold a remote telepresence call with each other. User A in red, user B in yellow, and user C in blue. So user A resides in this very large living room. You can see a perspective view on the left and a floor plan view on the right. User B, however, wants to join the telepresent meeting in her small office, and user C is working from the home, planning to meet in his bedroom space, which has a little bit more open area for the others to join. Okay, so let's look at the first problematic scenario. Okay, so this is user's A room, and he's hosting the meeting, which augments virtual avatars of user B and user C in an open area of this pretty big living room. With holding the same positional relationships with each other, in user's B space, however, she actually sees no one, basically no one. But if you look at the floor plan view on the right, the other 2 gentlemen are located outside her office. You see, when keeping the same positional relationships with each other, initiated in the previous scene, they just don't fit in user B's office. And more weird things happen in user C's room, where user A is looking like a ghost stuck in the wall and the dresser, while user B is also colliding with the furniture. Both remote individuals are in undesirable locations. Now you may ask, why do we need to keep the positional relationships constant? Why can't users have the option to force position and manually identify a desirable location for the remote avatars to be augmented in its space? So let's see what happens. Here we have the participants holding constant relationships with each other in all rooms. Now let's just allow them to manually force position remote avatars in their own preference to kind of fit in their spaces. So here's the problem. When user A is looking and talking with user C in his own room, shown on the left, in user's B room, shown in the middle, the direction user A is facing is not quite right. Instead of looking at user C, user A is talking to the wall, and the line of sight is incorrect. And you know, this becomes much more abnormal in user C's location on the right, where user A is supposed to be facing at user C, but instead is looking at user B in a complete other direction. So, you know, how do we address this challenge? And this is where our contribution kicked in our study of optimizing mutual spaces. Our first goal is to locate where users can walk and talk in their own room without colliding with objects in other remote rooms. We kind of do this by finding the mutual space between all the rooms. So let's see how that works. Say we have 4 rooms, okay? With 4 individuals planning to remotely meet each other in a spatial computer setting. First, we perform a semantic segmentation. Exactly like the previous study, we consider this as a given to the system to basically determine the bounding boxes of each object in the room. Next, we intend to locate standable spaces. And standable spaces are basically the volume of the room in which no object located within a human height range is present. Okay? And the user movement can be performed freely without a risk of colliding with the object in its surrounding physical environment. We calculate the standable space by simply subtracting the area of which the object occupies in a room from the room itself. Okay, so we do this with all the rooms. Next, we define a rigid body function G, where theta describes a transformation vector. We then run a genetic optimization to determine the optimal theta of each rigid body motion. So the area of the overlap between the boundary becomes maximum. If we map the mutual space back into the rooms, shown here in the blue area, when all the users stand or walk within the blue area in their own spaces, they are guaranteed not to cause virtual conflicts or line of sight mismatches within each other's spaces. Now, to add a little more flexibility, and increase mutual usable spaces, we can also define sittable spaces. Sittable spaces normally extend the standable spaces by adding areas where humans are able to sit on, such as sofas, chairs, and beds. Again, if we go through the same process, this time with sittable spaces, we observe larger mutual areas, okay? Which users can stand, sit, and walk and move around all those spaces without actually worrying to cause any unwanted collisions in other remote rooms. Okay, so we wanted to implement our proposed framework on some real-world data sets just to see how that works. And again, the Matterport 3D data set from scanned real-world data set is the one we chose. And over here, you see standable spaces are indicated in green and non-standable spaces are colored in red. And in this figure, you see sittable spaces are also visualized in yellow. Again, this is the calculation from the system. Moving on to identify the mutual space between these rooms you see in the figure, we kind of show how our genetic algorithm is gradually improving the results and expanding the area of the mutual space. And in higher generation values, we kind of see that this blue color, this blue space, is generated after 40 generations of the search between these rooms. But here's the thing. What if we want more mutual space? What if it's just not enough? And the identified mutual grounds are too small for the remote communication purpose. Say you want to play a game or inspect an object between participants. Where the object doesn't fit in the mutual boundary, can we move it? What do we do? That brings us to the second goal, which is, can we rearrange the furniture so that we increase the mutual space while minimizing the overall effort to do so? And the effort of each move is basically calculated by multiplying the distance of the object's transition by the object's weight. So in simple terms, moving a bed is considered to have a higher effort value than moving the chair for the same distance. So again, our goal is to slightly manipulate the room layout to increase mutual space with minimum effort. And to simplify this process for the user, we kind of define some increase steps, which each step has the goal to achieve 10% additional mutual space from its previous step, while maintaining the minimum effort to do so. Now let's take a look at the furniture manipulation system on a set of Matterport rooms example. Again, we have real-world scenes. We have a family room, an office, and a bedroom. And first, we extract the standable and non-standable spaces using the methods we kind of previously explained. And by utilizing our proposed mutual space identification system, we can locate the maximum mutual ground between these rooms. We then use a strength Pareto evolutionary solver basically to optimize for the two objectives. Effort, which is shown in this vertical axis, and the mutual area on the horizontal axis. Okay, so when we plot the rearrangement solution space, we can find the initial arrangement point of the Pareto frontier with the e-value of 0. Okay, so the effort is 0, and this is our mutual space without moving any furniture. Then, by increasing 10% of the area in each step as a goal, we start to find the rearrangement solution which satisfies the increased area goal and holds the lowest effort value in each step. So we're basically moving towards increasing the area while we're trying to minimize the effort to do so. So as you see over here, after 5 steps, we kind of show a significant increase of the mutual space while trying to minimize the effort required of the furniture rearrangement to do so. Okay, so the whole idea was for augmented reality telepresence. At that time, we didn't have the techniques to do avatar telepresence, but we kind of tried to show a better understanding of how the users would experience the system's output by deploying our proposed method with with the Microsoft HoloLens on augmented reality visualization. So for the target spaces, we scanned our office area at Corey Hall. All this happened before the pandemic hit. And in our office area, we had a conference room, a kitchen, and a main lab space for our experiments. We also provided the bounding box and semantic labels for the model. So we scanned them and basically labeled them. We then give this data to our system, and the system calculated the open spaces visualized here in green, and the mutual spaces also visualized in blue. And these are kind of the captures we have from the HoloLens in the kitchen. You see the mutual space boundary is with an offset of 40 centimeters on the ground, so users can clearly relate to it. And here you see the main lab in Corey Hall. The blue indicates the space that you can freely move around this boundary without causing any conflicts in the other rooms. Okay. Finally, a floor plan view of the space with different screenshots taken in different locations of the HoloLens headset. So of course there is limitations to our work. First off, in our current version, the increase in steps may not have any continuous relationships with each other. For example, in step 1, you might be moving a chair in a certain direction to achieve minimum effort, but if you then decide to move to step 2, it doesn't take into account steps 1 transformation. The next limitation is that our current system doesn't automatically take fixed positioned objects into account and should be defined manually. We also currently use generic data provided by moving companies to estimate the weight of an object, given its type. However, objects from the same type may have various weights, and therefore, it would be important to integrate correct values to achieve more accurate results. And finally, our future steps. We definitely want to perform more extensive user studies. We also hope we can develop this tool for cross-platform AR/VR interfaces and also use more robust floor planning methods for the furniture manipulation. And that's it. Thanks very much for listening and tuning in. Please feel free to contact us with any questions you have. We would be happy to connect with you guys and answer anything we can. I hope you have a very good day. Bye-bye.